This lecture is titled The Mathematics of Networks. The goal of this chapter is to solve for the most efficient way to connect a set of vertices, and some of the real-world applications pictured here include transportation roadways or railways, infrastructures such as sewer lines and pipelines, communication networks such as those used to connect phone lines and World Wide Web connections. And we even have some modern applications which include mapping of social networks or the mapping of the brain to computers, also known as AI. We'll start with some vocabulary. Our first term is subgraph. A subgraph is a graph that is made up of parts from another graph called the supergraph or the parent graph. Subgraphs cannot have parts not in the parent graph. So if I drag each of these over to the parent graph, we see that they line up with the parts of it. These are all examples of subgraphs. It's okay if it has no edges in it. It must have only parts that come from the parent graph. So a question is, can a graph be its own subgraph? And the answer is yes. As long as the parts in the subgraph are any of the parts from the parent graph, and that includes all of them, or it includes fewer parts, then yes, it is a subgraph. So which of the following are subgraphs of graph G? And we can see if I drag these over, all of the parts are there, so we would say A is a subgraph. If I grab B and drag it over, we see that this top edge here is not part of the parent graph. That does not belong. So as I pull it back, we'll say this is not. We'll say yes to graph A. We'll say yes to graph C and yes to graph D, because each of these consist of parts from the parent graph. So A, C, and D are subgraphs of G. B is not, and that is because it contains a part that does not belong to the parent graph, graph G. Our next term is a spanning subgraph. A subgraph that has every vertex of the original graph, but not all of the edges, is a spanning subgraph. Simply put, spanning means it must contain all of the vertices of the graph. So we see here we have 4 examples of spanning subgraphs. And the requirement is that all of the vertices, so we see the original graph has these 5 vertices. We expect those 5 vertices to be in each of the examples to be a spanning subgraph. They are, and then the number of edges could be from 0 to as many as all of the edges of graph G, but we have 4 different examples laid out here. Which of the following are spanning subgraphs of graph G? So the first thing I would look for is how many vertices do we need to consider? And we see there are 6 vertices in the parent graph. So anything with fewer than 6 or more than 6 would automatically be discounted. We see that all of these have 6 vertices. So far, they all look like they're spanning, but now we want to just take one more look to make sure that they are subgraphs, which means that their parts must come from the parent graph. So graph A, when I pull it over here, I see it has an edge that is not a part of the parent graph. This edge does not belong, so graph A is not a spanning subgraph. The rest of these will be, because it has all 6 vertices and the edges come from the parent graph. The only thing I'll make extra note of is that graph D is the only one here that contains circuits. And graph D is not a connected graph. But it is still a spanning subgraph. So I made those points about graph D because now we're looking at a next term, which is a tree. A tree is a connected graph with no circuits. And if I go back, we see that graph D violates those 2 requirements for a tree. So the graph must be connected, it must have no circuits. All of the examples on the left here are all trees. We see that all of these graphs are connected. A simple definition of connected is a graph that has a path between any 2 points. So if I look at these 2 points, I can get from one to the other because there's a path between them, so it is a connected graph. And that has to be true for any 2 points you choose in the graph to say that it's connected. All of the examples on the right are not trees. Here we see there's a circuit, so that disqualifies it. Here we see it's not connected. And also for graph F, it's not connected. So no circuits, and the graph must be connected to be classified as a tree. Next, we expand this to spanning tree. So if we recall, spanning means that it contains all of the vertices. And a tree means that there should be no circuits and it must be connected. So which of the following are spanning trees of graph G? A is not because it has a circuit. B is because don't misinterpret these overlaps as circuits. They are not circuits. We just have a bunch of edges here that are overlapping, but there's no points at those overlaps, so there's no circuit, and everything is connected. There's a path between any 2 points. So graph B is a spanning tree. C is not because it's not connected. D is, and E is also a spanning tree. They contain all the vertices, and all the vertices are connected. The properties of a tree that are textbook outlines. If a graph is a tree, there is one and only one path joining any 2 vertices. And then we have this extra comment that the converse is also true. So if we recall from our geometry class, after the if is the hypothesis, and then the conclusion follows. P is the hypothesis, Q is the conclusion. This is the shorthand notation that we learned back in geometry. A conditional statement is if P then Q. A converse statement is if Q then P. So the converse of property 1 states that if there is one and only one path joining any two vertices, then the graph is a tree. And all that does is it switches what we know with what we can conclude. Property number 2, in a tree, every edge of the graph is a bridge. This also says that the converse is true. So for property 2, if we were to use the converse, we would say if every edge of a graph is a bridge, then we can conclude the graph is a tree. We can read property 3 and take note that it does not say that the converse is also true. Property 3 says a tree with n vertices must have n-1 edges. There is no comment about the converse. So let's explore property 3. The converse of property 3 is if a graph has n-1 edges, then it must be a tree with n vertices. And property 3, we could draw it to be true, but we can also draw it to be false. So I'm going to say let n equal 5 and n-1 equal 4. So 1, 2, 3, 4, 5 vertices. If I draw this with 4 edges, we say, yes, this is a tree. This is a true example, but we can also draw a false example. So if I take these 4 edges out here, now I have a circuit and it's disconnected. So property 3, the converse statement, is not true because we can draw a counterexample to it. In order for it to be true, it must always be true. So again, property 3 is saying we're starting with something that is a tree and has n vertices, so it must have n-1 edges. Property 3 is true, and that's because tree is given in the hypothesis. Let me go back to the slide so we can see property 4. A connected graph with n vertices and n-1 edges must be a tree. And the reason this is true is because this word connected was thrown in there. If it has n vertices and n-1 edges and it is connected, it must be a tree. And you can go back to the example here and see that, well, if I let n be 5 and n-1 be 4, and I add connected, then I don't have the option to draw it as a circuit with a not connected graph. It has to look like the example on the left because the word connected was added to the hypothesis. Another value we will be calculating is called the redundancy of a graph. So if a graph has any circuits in it, it then has redundancy, and those are extra edges that keep the connection even if we lose an edge. So to see an example, here we have a graph with 5 vertices. It has 1, 2, 3, 4, 5, 6 edges. And the formula down below says that redundancy can be calculated where m is the number of edges in the graph. So we'll say r is equal to 6 minus, and then we have parentheses, n, where the n is the number of vertices in the graph. Vertices is 5. In the parentheses, we have a minus 1. And now we can say redundancy is 6 minus 4. Redundancy is 2. That means we have 2 extra edges. If we were to remove 2 of those edges, then we would end up with a graph that looks like this instead. And we say everything is still connected. We just don't have those extra edges to fall back on if one of the edges in my tree should happen to fail. So another way to think of this number is how many edges do you need to remove to turn the graph into a tree? So find the redundancy value for graph G. So again, you can think of this as how many edges do I have to remove to convert this graph into a tree? Well, if I just draw the minimum for connecting with no circuits, I'll keep those 3 red ones, and I would get rid of these 3. I can say R is equal to 3. That was doing it visually. If I use the formula, there was a total of 6 edges. There's a total of 4 vertices, and R is 6 minus parentheses 4 minus 1. R is 6 minus 3. R is 3. So this is by formula, and this we solved graphically. Here's a sample problem that we can get, which is testing if we understand how to apply the properties that we discussed for trees. So answer T if it is definitely a tree, explain why. Answer N if it is definitely not a tree, and give a counterexample. Answer M if it may or may not be a tree, and give an example of each. So we'll start with 9a. G is a connected graph, and it has 8 vertices, and every vertex is even degree. Well, once we see that, we can recall from our earlier chapter that this is the requirement for an Euler circuit. So the graph must have a circuit in it, therefore it is definitely not a tree. Let's look at 9b. G is connected. It has 8 vertices. There are 2 vertices of odd degree, and all of the others have even degree. So I can connect this 1, 2, 3, 4, 5, 6, 7 edges. Everything's connected. I see that these two edges have degree 1, and all of the rest of these have degree 2. So that's an example where it is a tree. And then I can draw this graph again. It's connected. There are two vertices of odd degree, and all of the other vertices have even degree. And here we see it is not a tree because now we have multiple circuits. So the answer for B, 9B, would be M, and that is that it can be drawn either way. I've provided a drawing of each. And then 9C, G is a connected graph and it has 8 vertices. The degree of every vertex is either 1 or 3. So once again, I'll draw my 8 vertices. I have my 1 degree vertices, and that gives me a 3 degree. Right here I have a 2 degree, but if I add a line, that becomes a 3 degree. And then here I have a 2 degree, and I've just made it a 3 degree. So this is not a tree. So 1 degree, 1 degree, 1 degree, 1 degree, 3, 3, 3, 1. This one is a tree. So once again, we would say M can be either. See the drawings. So it requires some experimentation with drawing these out and showing that given the description, words like connected make us have all the vertices connected, and then determining how we can draw it with the restrictions they've given us, such as 2 vertices of odd degree, all others have even degree, or every vertex is either degree 1 or 3. We had to draw these out and find examples and say, can I draw an example of it being a tree and not a tree? And if that's the case, you answer M may or may not be a tree. So here's another one that you can work out. Pause the video, try it on your own. And then after you're done, you can unpause it and compare your answers with mine. G is connected and has 10 vertices. Every vertex has degree 9. So definitely not a tree. And this is the definition of a complete graph. So a complete graph on 10 vertices. Every vertex will have degree 9 and be connected. 10b, G is connected and has 10 vertices. One of the vertices has degree 9, and the other vertices have degree less than 9. So we would draw that out. My hunch is that it will be M, and I will say, how can I draw this? So there's my 10 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is a tree where one vertex has degree 9, and all of the others have a degree less than 9. In this case, all have 1. So this is a tree. So they didn't give any restrictions as to how many edges, so I can connect these in all different ways. And I'm creating a bunch of circuits when I do this. So this is not a tree. So for 10b, the answer is M. See the drawings, one of each case. 10c, G is connected and has 10 vertices, and every vertex has degree 2. That's how it would have to be drawn, and we see it has a circuit, so it is definitely not a tree. Draw a spanning tree for each of the following. So what we're going to do here is say, well, how many edges do I have to take away to break up all of the circuits? And now we see we can draw point A down to D, from D to F, from F to E, from F to C, from E to B, and I need to take away 4 edges altogether. For part B, we can start at vertex B, go to A, and again, our goal is to draw a subgraph, which is a tree. And there's more than one way to draw this, but altogether we have removed 2 edges. So we can say that A had a redundancy value of 4 and that B had a redundancy value of 2. Here we have an easy one. It's a simple circuit. Take one edge away, and we have a tree then. And here for part D, D is already a tree. The redundancy is 0. So this concludes our lecture. Watch the video again, take notes, and then try the practice problems I posted. Send me questions in email if you have any.